In this video, I want to talk about some integrals in some integral theorems that we've talked about in chapter 4. So this is just a bit of an overview, no new material here. I just wanted to recap all the integral theorems that we have and kind of write them down in one place just for kind of safekeeping and making sure that we have everything all straightened out. So the first theorem says that if G is a region, so if G is an open connected set, if gamma is a piecewise smooth curve that's in G, and if little f is continuous with an antiderivative, then the function of f of z over gamma is going to be this quantity here. So it's the antiderivative capital F evaluated at the endpoints of the path. So what this tells you is that this quantity is going to be the same regardless of what the path is, as long as you start and stop at the same point. So it doesn't matter if it's a line or part of a parabola or a spiral. If you start and stop at that same point, gamma of A and gamma of B, then you're going to get the same integral, again, as long as the rest of these conditions are met. And in particular, if this is a closed path, meaning that gamma of A and gamma of B are equal, then the integral will be 0, again, as long as little f is continuous with an antiderivative and as long as gamma is piecewise smooth. Okay, so that's the first thing. So if you have a continuous function, you get path independence. The second theorem says is called Cauchy's theorem, and it says that if you have a region G, if f is holomorphic on G, so remember that that means that it's differentiable not just at all points in G, but in a small neighborhood of G. Since G is open, it's basically saying the same thing. And if gamma naught and gamma 1 are piecewise smooth curves that are homotopic, so remember that that means that there's a continuous deformation between the two paths, then the integral of f over gamma naught is equal to the integral of f over gamma 1. Okay, and so this is kind of the homotopy equivalence theorem is the way I think about it. So if you have two curves that are homotopically equivalent, then the integral of f over one of them will be the same as the integral of f over the other. Now, this seems like an obvious statement when gamma naught and gamma 1 start and stop at the same point, but they don't need to. So for example, if you're integrating over a circle, what this theorem says is that that's the same as integrating over a square, as long as those two curves are homotopic in some region G. Okay, so this is Cauchy's theorem. And then finally, the most recent one that we've talked about is Cauchy's integral formula. Cauchy's integral formula says that if you have a region G, if gamma is positively oriented, simple, closed, and piecewise smooth, and if W is inside gamma, and if gamma is contractible. So if gamma is homotopically equivalent to a point in G, then you have the following formula. So f of W is 1 over 2 pi I times the integral of f of z over z minus W dz, okay, where you're integrating over gamma. So this is Cauchy's integral formula. Okay, so three, again, very different results. They might feel a little bit like the same thing in a certain sense, but anyway, so three very different results here.